So a very good afternoon to all the esteemed gathering here for the second week of teacher enrichment workshop entitled as Differential Equation and Mathematical Modeling in collaboration with the National Center for Mathematics, a joint center of IIT Bombay and TFIR Mumbai. I would like to request all the participants to please keep your mic at the mute mode. So without wasting any second of this expert session, now we proceed further for the continuation of today's session. So today we are very privileged that our speaker, Professor Kapil Sharma sir, has already joined. So now I would like to request Professor Kapil Sharma sir to please start the session.
Thank you, ma'am. So we will start where we left yesterday.
Right, sir.
So I have given some assignment that find out some drawback of Taylor's method and Picard method, so that we would be interesting to investigate some more method and to get rid of that drawback. So anybody have? So please tell me. So please tell me some of the drawback of Taylor's approach and Picard. Hello, Pankaj. Anybody tell anything? Neeraj, do you have any idea? There should be some drawbacks which would motivate us to, or no, not all means us who develop other methods, who move to the new another class of method, namely known as the step marching method or discretized method. So we should first understand what are the drawbacks. I think many of you were discussing yesterday. Okay, so I will try then the limitation of Taylor's approach and Picard. What are the advantage of these method or beauty of these method? Anybody can tell? Because they by these approach we can generate a method with desired accuracy. Am I right? This is the best one.
Yes, sir.
Thing in the approximation theory, and also because by these methods we
Sir,
have,
in my opinion, the drawback is like that if we have the larger terms, so the complexity getting worse.
if we have
The larger terms to approximate up to fifth or sixth or seventh, so the calculation gonna be very big.
yeah, that is also I mean it's not a easy task.
Yes, sir.
Yeah.
Truncation error will be increased in that case.
Yeah. And another beauty of these method, but you will see when you compare this drawback, because now we have very sophisticated tools with us, so we can do that calculation using Mathematica or other thing. But another beauty of this one is that we are getting the solution with the desired accuracy, which is the best thing in approximation theory. And the second one is that we are getting the solution on the entire domain. Am I right? We are getting the continuous solution. Am I right? So these two are the beauty, or we can say that advantages of these methods. But if you see what we are doing basically, if we observe in the Taylor's method, we start with the Taylor's method. So if we talk about the truncation error, I mean, all of you are aware about that. When we are dealing in the approximation theory, so there are two type of error we have. Am I right? Number one is the truncation error. Am I right? Do you remember truncation error? Many of you are, I think most of you are aware about this terminology.
Yes, a truncation error is there.
Truncation error. And the second one is the round off error. Am I right?
The two types of error, yes, sir.
Two type of error in approximation theory. But I basically renamed these terminology because truncation error seems to be that we are truncating something, and because of that it's occurring. But this is not the case. Like if you remember in Taylor series, we are truncating the series after finite number of terms. But I name it human error.
That would be a terminology better.
Human error.
Because we are going to calculate that things. Sir, if possible, please share your screen as well.
Oh, okay, sorry. So we call it a human error, and the second one is the machine error. So now I will say why we are calling it in that way. Now it's visible?
Yes, sir.
Yeah. So it's a machine error. I'm just denoting this one. Machine error. So why we are calling it this human error or machine error? Because when we are, I mean, going to tackle a mathematical problem, and of course we are using the method which give the approximate solution. So what is error is one error is occurring due to our limitation. Am I right?
Yes, sir.
What is our limitation? Basically our limitation is that we are not able to solve the problem exactly. Am I right?
The exact one
error,
analytical analyticity is different and calculation is different. So that error comes into the picture.
Yeah. So because we are not able to solve, or we don't have any procedure, any method to find the exact solution of the problem. So because of that, basically in some way we are approximating the problem. Am I right? Or we are making some approximations, and because of that approximation there would be some error. So the error is occurring due to the human limitation, is known as the human error, or we call truncation error. One thing, because nowadays, I mean, it is not possible that we do the big calculations on by hand. So we use some machine. Am I right? Whether it's a calculator,
yes,
it's a computer or calculator, any machine we are using. So once we are using machine, so machine is also a finite machine. Am I right? It cannot store the number with a infinite memory. Am I right? Suppose I want to, if I ask you that store the number this 1 by 3. Am I right?
Yes,
when you store in a machine, in computer or in calculator, so it will not be the exact one, because it's a non-terminating. I mean, take its the decimal representation, so it will be non-terminating. number you have. So in that case, it will store the number up to finite number of digits. Am I right? So
Yes, sir.
once if we are not using any machine, so then this type of error will not be there. Am I right? If we are not using any machine, because when we use machine, so that machine crunches the numbers. So that's why we call it human error and machine error. So now if I am talking about only the human error, in case of this Taylor's approach, so what will be the truncation error or human error in that? If I denote that by T, so T will be if we write the Taylor series with the remainder form, so then it has n power h power n plus 1 divided by factorial, or I think n it will be, because if we are casting the first h f prime, yeah, factorial n and f n plus 1th derivative at xi. Am I right? And basically what is h we are taking? H is x minus x naught. This thing is clear. Power n,
yes, sir,
divided by factorial n and this is f n plus 1th derivative of n. Now suppose if f is sufficiently smooth, I mean to say that f belongs to C n plus
n plus 1 functions.
1. Am I right? C
Yes, sir.
1 I the interval domain. It's fine.
Yes, sir.
And this thing is clear. So it means its n plus 1th derivative is finite, means it's bounded. Suppose it is bounded by m. So now we have this is equal to
So less than or equal to what?
x minus, yeah, less than equal to m, because we are taking the bound.
Yes, the bound is coming up.
Less than equal to x0 n divided by factorial n m. Am I right? Now you look that on what t depend. You'll see here n is a constant, n is a number, m is a number, x naught
Also a constant.
yeah, x naught is also constant. We suppose this is start from here, x naught. So now you see this error is depending
on the value of x.
On x. What does it mean? It means that initially in the simulation, initially we are getting a very good result, but after some time we are getting worse and worse result. Am I right?
Yes, sir.
So it means that these methods, or the methods obtained using the Taylor's approach or even Picard approach, so these are biased toward initial or starting point. Initially it will give you a good result, or it will give the result with the desired accuracy. But after some time, suppose you need to run your simulation for a month, so
Yes,
after
sir.
some time you will get the very bad result. So we are not interesting. So this is very, I mean, big problem, or we can say that we are not interesting, or we can say that it's not a feasible condition, because initially you will get the good result, but after some time, but we don't know what is the meaning of some time. So that's why these methods, both Taylor's and Picard, the method obtained using Taylor's and Picard, are the biased towards the starting point. So this drawback motivated the researcher to research the method which give the error uniformly over the entire domain. So then we came to, or then there was a birth of discretization method, or step marching method, or step marching methods. So why it's basically happening? If you observe that, suppose we have this is our domain, from x0 to capital X. I have to take the approximation on this domain. I have to simulate our problem on this interval x0 to capital X. Am I right? So basically what we are doing, we are we are approximating the things, whatever we are doing, on the entire domain. Am I right? And if this is a bigger one, so then you will see that, and you know the basic principle. If we are approximating things in a small part, so we will have less error. In if you remember, in the case of Riemann integration, we divide the entire domain into small
Subintervals.
subdomains, and rather than finding or the
On a whole domain, if you
rather than approximating the curve on the entire domain, we are approximating the curve on the small subdomain. And as that this the width or of the subdomain is going to be 0, so we are getting to we are converging to the exact integration value. Am I right? So same thing happen here. Rather than make approximation onto a bigger one, entire domain, you divide the domain into small part. And basically in initial value problem, what we do, we divide the domain, we fix the size of the subdomain, and using this value, using this value initially, we are predicting the next one. Then using this value, we are predicting the next one. Using the previous value, we are predicting the next one, using some approach. Am I right? Whatever approach we use, that is immaterial, but we are doing
iteratively we are moving.
Pardon?
Iteratively we are moving from 1 to 2 and so on and so forth.
Yeah, basically not exactly iteratively. When we are, I mean, calling it iteratively, so then basically we are, I mean, going into an infinite loop. Am I right?
Yes, sir.
But here it's a finite one, because
Okay.
suppose we divided this, yes, it is
Five
let's
times.
say the 10,
Finally.
and we have taken the our step size 1, so we will reach up to here in 10 step. Am I right? So not
Yes, sir.
iterative procedure, but we can say that in steps. Am I right? In
Yes, sir.
steps. And we are marching in the forward direction. Am I right? So that's why these methods are also known as the step marching methods. And of course we are discretizing the domain, ultimately at the end. So these are also known as the discretization method. But when we deal the boundary value problem, so then of course we have to discretize. In that case there is no way to going step by step. But in the case of initial value problem, we can analyze these in that way also. So this thing is clear.
Yes, sir.
And now basically whenever we are making the approximation, so we have the same size of the domain. And if we feel we have, I mean, error is more, because to retain the property with the desired accuracy which we have in the case of Taylor's and Picard, so that can also be here. If we feel after, I mean, taking the step size is this one, we feel we are getting more error, so we will again take smaller step size, and then error will be reduced. Am I right?
Yes, sir.
Yeah. So in that way we do the computation, and this is the motivation for developing the step marching or discretization method. So now we again come to the our basic problem. Y prime is equal to fxy. So we are moving to I mean, where we left at the Picard one, so we will start from there. Yx basically is equal to y0 plus integral x naught to x naught to x f of x, or if you take xi, xi y xi. This thing is clear. So now our basic motive to solve or to find, to evaluate this integral. Am I right? And you can see that basically f nothing, f is y prime x. Basically f is nothing but y prime x. So if I write I mean, because if y is a function of x, so then of course y prime will also be a function of x. So rather than if I am taking this f, I can take it in place of this f, I can write some another function, call it so g. What is g? Basically g is y prime x, so this is dg. Yes. So basically now if you see, this integral is nothing but, suppose this is the curve of gx, and it is from and this is x0, and this is, say, x. It's fine. So basically this integral is nothing but this area. Am I right?
Yes, sir.
Now basically we need to find this area. So rather than solving our initial value problem y prime to f, so now my objective, and this is nothing but this is the curve of G. Am I right? So my problem is transform. My problem is transform to find this area, area under this curve. Am I right? So how we should do that? Now first we should see that where we are facing the problem. Am I right? And then we try to.
The nature of G is unknown
Pardon?
to us. The nature of G is unknown to us, sir.
Yeah.
That is the problem here.
Yeah, that is the problem. Basically, if you see this geometry, in geometrically, if we talk about, so then this, if you observe that we know area. Now we should see that. I mean, what type of geometry we know the area? We know area of the rectangle.
Rectangle, square,
Am I
these
right?
are the things. Yes, sir.
Yeah, rectangles. Square is also. I mean,
For a well-known figures.
class of rectangle, we can say that if all the sides are equal. So we know the area of the rectangle. Am I right?
Yes, sir.
But here, if you observe that, except this line, this curve,
Above the curve, yes, sir.
yeah, all are the straight line. So this curve is creating the problem. So that's why basically we will approximate this curve by a straight line.
Straight
Am I
line.
right?
Yes, sir.
So now we can approximate this in two ways. One is this way. Am I right? From the lower side. So if
From
you,
the lower or from the above?
yeah, from the above. So if you see, this is the this height is G0, means G0 G at. Am I right? G0 is G at x0. Am I right? And this is basically, this height is this up to here. This height is
G at what?
Gx. Am I right?
Yes, sir.
Gx. G at x. This thing is clear.
So the remaining one is Gx minus G naught.
This one is, pardon?
Difference is now we are looking for here.
Yeah. But basically, my objective to find the area of this figure. Am I right?
Yes,
But
sir.
now I know that I don't know the area of this geometry. So that's why I have approximated this geometry by the known geometry, by this rectangle. Suppose
Yes,
now
sir.
I approximate this by this rectangle. So then what would happen? Then this equal sign, or if I fix that, suppose rather than x, I fix x1. Suppose I fix x1, where this x1, x1 minus x0 is h. It's fine. Suppose x1 minus x0 is h. So in that case, now this equal sign become inequality. Once I make this approximation, so this is equal to y0 plus. Now what is the area of this rectangle? Base into height.
Yes, sir.
This is the base. Am I right? And this is the height. So h times G0. Am I right?
Yes, sir. H times G naught.
G0. H times G0. It's fine. Now what is G0 basically? G0 is nothing but the value of G at x0
At x naught.
and the G, yeah, f0. So this is basically is equal to, this is basically is equal to y0 plus h F H F0. Am I right? So we have this one. Now you look, this is not equal to y at x1. Am I right? This is not equal to y at x1. Whatever we are getting, so we are calling it, this is y1. So y1 is not equal to y at x0. Even this is y1 is an approximation of y at x1. This thing is clear. So that's why we will write y1 is equal to y0 plus h f0. Now suppose this is our entire domain. This is our entire domain. So rather than taking this x0 to x1, if I take a journal from, say, this is x n and this is x n plus 1. Am I right? X n plus 1. So we can write that x n plus 1, x n plus 1 will be equal to y n plus h f n. Am I right? So now you put n equal to running from 0 to capital N minus 1. If you divided the entire interval into the n capital N subinterval. This thing is clear, and this is nothing but, if you remember, what is this? This is the Euler forward difference method. Am I right?
Yes, sir.
So similarly, now suppose now I can make approximation a different way. So in the reverse direction by reverse rectangle. So that is also an approximation to the same geometry.
It the backward.
Right?
Yes, sir.
So in that case, what we have, if we write this one, so then we have y0. Then I'm writing from here. Then we have y0 plus h g1 rather than
Yes,
g1 rather than g0. We have g1. G1 means f1. Am I right? This thing is clear?
yes.
So if we write this formula in the journal form, so we have y n, am I right, plus, tell me, h times
H of f of n plus 1.
F of n plus 1. This is known as the backward n plus 1. Why we call it backward and forward? First one forward and second one backward. Anybody can answer? We call second as a implicit also. Hello? So please answer. Try to participate. All of you know. Or if you don't know, so just try to dig out from here the figure what we are doing. If you look
at the values, because we are starting with the beginning values, that's why it is.
Basically, we are starting from here and we are stretching this value in the entire domain in forward direction.
Yes, sir. That's why they are forward.
It is known as the forward. In this, we are taking this value and stretching back in the backward
direction. Yes, sir.
In the interval. That's why it is known as the backward Euler. And we know this is implicit. First is known as the implicit, and second is known as the explicit.
Explicit.
Why? Because you need see what is unknown here. Yn plus 1 is unknown. Am I right? And on the right hand side, everything is known. So unknown is written in explicit form. Am I right?
Yes, sir.
So that's why it is known as the explicit formula. And here, if you see, unknown is sitting in the right hand side also, because what is y fn plus 1? Fn plus 1 is nothing but f x n plus 1 comma y n plus 1. So this is sitting in implicit form. So we can, this is an implicit formula. Am I right? For calculating yn, because we don't know the y. If y is a linear function of y, sorry, if f is a linear function of y, so in that case you can do that. Am I right? You can make it explicit. You can find out, but suppose it is a non-linear function,
then it is difficult to separate.
Yeah, difficult in most of the case it will not be possible. Am I right? So that's why it is implicit. So now I'm giving you the exercise and I'm giving you 5 minutes time. Now find out the third one. What is the third one? Now find the third one. What is the possibility for that? So please do that on your notebook. I'm just coming in 5 minutes. So please do that.
अभी पता चल जाएगा. I think there is internet problem.
No, sir. 5 minute break, hai, ma'am.
Hello.
Sir,
Yes, sir.
Yeah, yes, ma'am. Yes. So, did you complete that?
The
Hello?
simple differences, sir.
Yeah. So, tell me, what is the, I mean, other way to?
We can make it a central difference. So we can make a thin line. We'll go either backward or forward. Both from the
Pardon?
difference. We have to reach out at some point T in between x0 and x1. So we can move either in forward
No,
direction or
but I
backward.
think don't go in that way. Yeah, you can. I mean, find in that way. Also, take any value here.
Yes, sir.
But in that case, we don't know whether we are getting the better thing or not. That
Yes.
way. Also, the another better way, whatever we have right now. I mean, to do that. Yeah, this is also a one way, but in that way, I mean, it could be the similar thing. But anything better can we do to approximate the area of this geometry?
Or,
By trapezium, we also know the area of the trapezium. Am I right?
yes, sir. We can fit the trapezium in this.
Yeah,
dressing gap.
we can approximate this
In
curve
the gap,
in
we
this
can fix
way.
it.
In
Yes.
this way, am I right?
Yes, that would be the better approximation.
That will be a better approximation, whatever we have till now. Am I
Yes.
right? So, what is the area of trapezium? Area of trapezium will be this is y0 will remain the same. Y0 plus h by 2
H by 2.
by
Yes, sir.
h into average of the
Average
parallel
of the
side.
parallel.
So I'm writing this, or I can write in that way also.
G1 plus G0 upon 2.
Yeah, f0, yeah, g naught plus g1
G1 upon 2.
upon 2. So in that way, we have generated the
Central difference.
trapezium,
Trapezium.
trapezoidal rule, if you
Yes, sir.
know. Am I right? So in this way, we do that. So we can tell the student in that way. All these three methods are generated in this way. If write this in terms of this thing, in the general form, so then we have this is equal to y n plus h by 2 h by 2 fn plus fn plus 1 fn plus 1 fn plus 1. So this is the first one is the for Euler forward, this is the Euler backward, this is the trapezoidal. This thing is clear. And if we I think if you see do the error analysis of these three methods, so you will see that in the first one the first one is of order h, second one is of order h, and the third one is of order h square. I think in the discretization method, if you are aware about the concept of the convergence, am I right? Convergence of a method, am I right? So how when we say that a method of order p, we say that a discretization method of order P if the error En can be written as C, some C is constant, H power P, H power P, where this H is known as the step size or discretization para or discretization parameter or mass parameter, this H. So then we say that our method is of order P. This thing is clear. So in the case of Euler backward and forward, this comes out to be C times H, and in the case of trapezoidal, it is coming out to be, error is coming out to be C H square type. This thing is clear? Hello? So any other improvement can be possible at this stage, because we are getting the method of maximum of order 2. So now our objective when the further research was advances, so in that to increase this number, am I right? If it would be 3, so then order of convergence 3. If it would be 4, then order of convergence 4. So now look, so now our objective, because here we have motivation, of course it's these are Euler method, it's good, then backward Euler also it's good, and this trapezoidal is far better than both, but there is a chance of improvement. If we are increasing that, so then we are getting this error will be quickly decrease. Am I right? Suppose we are taking h equal to 0.1. H is equal to, we are taking h equal to 0.1. So in the first case, what will be the error? Error will be of order 10 raised to the power -1. Am I right? And in the second trapezoidal method, the error will be of order 10 raised to the power -2. This thing is clear? Hello? So this thing is clear. So now you would say that, okay sir, it's fine that in the first case we are getting error of order 10 raised to the power -1. In the second case we are taking we are getting error of 10 raised to the power -2 if we take h equal to 0.1. But if we take h equal to 0.01, then in the first case also we are getting the same. Then what is the how, or what is the benefit of trapezoidal? But if we feel that the error is less, so we can take h to be more, lesser. So then what would happen? Hello? Can anybody answer to this? So just try. What is the need of higher order method? What is the need of generating or developing the higher order methods? Am I right? First we should understand, then we will move. But if suppose in the case of trapezoidal, we are getting the error of order 10 raised to the power minus 2. But in the first case, rather than taking h equal to 0.1, if we take h equal to 0.01, so then we are getting the same order of error. Am I right? So in taking h to be smaller, is there any problem somewhere? Yeah, is there any problem? Okay, let's see. Where is the problem? If we take this is equal to, am I right? Suppose we have to calculate, we are interesting to find the value at this point. Am I right? If I take h equal to 0.1, suppose it 0.1 is here. Am I right? So suppose I take h equal to 0.1. So or okay, for simplicity, if I take rather than here, yeah, if suppose this is from here to here, this distance is 0.1. Am I right? Am I right? So if now if I need accuracy of order 10 raised to the power minus 2. So suppose I use I use trapezoidal rule. So in that case, this is x0. If I take the x0 and this x1, h if I take 0.1, so this is basically, this will be the x1. Am I right? This will be x1 and I'm getting the desired accuracy. Now suppose I use the first one or one of the Euler method. So in that case, what would happen? In that case, to reach here, how many steps I need to take? Because now our h is 0.01. So how many steps I need to take to reach here? Hello, please answer. When h is equal to 0.1, so then I need to take only one step. Yani y1 will give me the answer. Am I right? Now if I am using step size 0.01, so then how many steps I need to take? 10 steps. First I have to calculate this, then this, then this, then this, then this, and then I will reach after the 10 step. Am I right? Hello. अब ये भी नहीं कह सकते मैम से कि भी कुछ चाय वाय पिलवा दो पार्टिसिपेंट को, है या तो ये है कि भी गूगल के थ्रू भेज दे मैम कुछ।
सर ऑनलाइन भेजा है, शायद मिल जाए।
तो यही है, क्योंकि मुझे स्लीप फील कर रहे हैं पार्टिसिपेंट आज।
वही सच्चाई मिलता तो सब एकदम एनर्जी के साथ
ठीक रहता माहौल। So anyway, let's try. But if it is take, so what is the problem now? To reach here, I need to take 10 steps. And in the case of the trapezoidal, we need only one step. So I mean, lot of computation you require. So this is not the feasible. So we need to, I mean, always need to, or always interested to develop a higher order method. So now here, if you see any further improvement can be done. Now, how we should get the better result? I mean, one way is that generally we used to do in research कि भाई एक पेपर में हमने लिटरेचर सर्वे किया, भाई उसने जो एक ने लगाया था फाइनाइट डिफरेंस, एक ने स्प्लाइन लगा दिया, फिर स्प्लाइन भी लग गया, फिर देखा यार फाइनाइट एलिमेंट नहीं लगाया, दूसरे ने फाइनाइट एलिमेंट लगा दिया है. So but that would not be the thing. When you are doing research, so you should see that what are the drawback and how we will get rid of this drawback. When you are doing the literature survey, so you should do in that way. You should try to find the gap and how to fill that gap. भाई ऐसा नहीं है कि वो गड्ढा भरना है, वो दूसरा उसके गड्ढे की जगह वो साइड में दूसरे गड्ढे में चले गए. So that's why we should see. So now we should see that whatever we have done to get better order of convergence, so what we need to do, if you observe what we did, basically what we are doing in this case, if you see, so then we would be able to, first we should understand that what we have done. So basically, if you observe in both the cases, or in all three cases, we have approximated this curve by a straight line. Am I right? One way is this one, second way is this one, and third one is this way. This thing is clear. So I think now there is a theorem by Weierstrass in approximation theory, and that is the backbone of the approximation theory. I should say that any continuous function can be approximated by a polynomial. Am I right? With desired accuracy. Am I right? If we have a function for given epsilon, if we have a function f which is continuous on an interval, am I right? Then corresponding to f for given epsilon, for given epsilon, I can find there exists a polynomial. There exists a polynomial Pn such that norm of f minus Pn is less than epsilon. Am I right? What does it mean? It means that you take any epsilon, I will you give me any epsilon, I will give you a Pn. And what is Pn? How we will get the Pn? We will increase the degree of the polynomial. Am I right? As you are taking smaller value of epsilon, I will take bigger and bigger value of n. So it means that if rather than a straight line, if I would approximate this curve by a quadratic equation or quadratic polynomial, so then we will get the better result. Am I right? भाई ऐसा करो कि घर पे ही चाय वाय ले लो कुछ. Are available or just join the meeting and leaving, doing something else? कुछ तो respond करो, otherwise it would be very boring. Otherwise I will give you some exercise if you are not interested in that. So we can do that assignment. but it would be very interesting and useful when you teach to the student, rather than just giving the formula that what is this is the Euler method, this is a backward Euler method, this is the trapezoidal rule. And when you move to the multi-step method and Rangakuta method, this is the RK4, this is RK2. Rather than we should teach in that way, that they should be aware. Many of you would be teacher. So now how we will do that? Now I have to approximate this curve by quadratic equation or quadratic polynomial. So first you should see that to fix a straight line, how many information you require. I mean, if you interpolation theory, if you want to interpolate a polynomial, a straight line, so how many information you require? What is the equation of polynomial? Straight line? Ax plus b. Ax plus b. Am I right? This is the equation of first degree polynomial. Am I right? This is the most general form of first degree polynomial. भाई यस नो कुछ तो बोलो. है कि नहीं है? सरफराज, आर यू अवेलेबल? मुझे लगे or should I do error analysis? In what you are interesting? We have 1 hour left, so if anybody, so we can discuss that rather than moving in further. What I should do, ma'am? If you are not able to get in this way, so I can give through presentation. So this is a first degree polynomial. Ma'am, should I move further or what should I do now? I don't think in that way it would be a wastage of my time as well as a participant. If you are interested, so then I will move further. Otherwise, we can leave. You can do some exercise. Am I audible? Hello?
Yes, sir.
Yes, sir, you are audible, sir.
But nobody is responding. Then how it would be possible? I mean, it's fine. Maybe we are not aware about anything, but you should respond. If you will not respond, so then how I will teach? I mean, this is not the case that I have to just deliver the things. If you feel like I can use, I can teach from some notes. Is there? I can discuss the error analysis of these method if you are not interested in that. Otherwise, my motive that how we are moving to, I mean, from this Taylor's Picard to discretization method, and in discretization method from these Euler, backward Euler, trapezoidal to Rangakuta method and multi-step method. Only these things are there. So if you feel whatever we have done, we should do the error analysis. So I can use some notes and I can discuss that also. So in which direction we should move? I think some of participants should tell, at least who are involved in some way, either teaching this numerical analysis or just doing research. So only then it will be possible. So if this is a equation of line or straight line which we are doing, and you see to fix this straight line, so we need two information. Am I right? To find the value of A and to find the value of B. And if you see here, we have that. We have that, we know that at x naught f0 is given, so we know f0, and at x1 f1 is given. So by these two we can fix the straight line, or we can interpolate the straight line. Am I right? So now we need to get some improvement. So for that we need to approximate this curve by quadratic curve. So ax square plus bx plus c. Am I right? This is a
Yes, sir. Yes, sir.
equation of a quadratic polynomial. Am I right? So as by I mean using the theorem of Weierstrass, we know that if the degree of the polynomial will be more, so we will get better approximation. So using that, so we now to improve more accurate result, so we need to approximate this curve by quadratic polynomial. So in quadratic polynomial, so now how we should approach that? Because now only we have two information, so we need to interpolate this I mean quadratic polynomial, we need to have more information, I mean at least one more. So suppose if we go in that way now, now you look that if we are solving, we have to reach basically up to here, and we divide into a uniform step size, this one, and this one, and suppose we reached up to this point, we have to calculate it at this point. So this is say x n. So when we solve this, means we have value at this one yn, this is approximate value of y at xn. Am I right? And so this is y0, and this is y1, and the previous one will be yn minus 1. Am I right? Now
Yes, sir. Yes, sir.
Yeah. Now suppose we have to calculate at this point yn plus 1. I have to calculate yn plus n plus 1. yn plus 1 we have to calculate. So earlier we are using only this value, these two. Am I right? So we said that we would be able to only interpolate a linear one. So if we need to interpolate quadratic polynomial, so we need more information. So if you see that we know this at this point also, we know the information, am I right? At this point,
Yes, sir.
we know the information. So if we wish to interpolate the quadratic polynomial, so then we can use these one. Am I right? These
Yes, sir. Yes, sir.
three value, and in that way we will approximate the curve by quadratic polynomial, and we will get the better result. If we wish to have cubic, we wish to interpolate by a cubic polynomial, we require 4 information, so we can use this one,
Yes, sir.
this one, and this one. And you heard that till now we were using only the one step, only this one. Am I right? 2 value we are, using. So that means only these 2 value we were doing that. Am I right? So only single step. So that's why the Euler method, trapezoidal Euler method, or backward Euler method are known as the single step method. If we are approximating, or we are using this value also, so now in approximating the value yn, we are using 2 step. Am I right? This and this step. So this is known as the multi-step method, 2-step method. Or if we are using more than 1 step to compute the next value, so the method, class of methods, or class of step marching methods is known as the multi-step method. So in that way, the multi-step method were developed. If you are using the n value, so you can interpolate a polynomial of degree n minus 1. This thing is clear? So in that way we have generated that. So now I am okay. I am using some text. I think then things would be better. I hope so. So 1-step method, we till now we have studied 1-step method, or Euler's method and its relatives, which are known as the theta method also. In theta method means if we take theta is equal to 0, so then we are getting, you look here, if we are taking theta is equal to 0, so we are getting explicit method, gn, g at xn will be there, h g xn means h fn. If we are taking theta is equal to 1, so then we are getting h g at xn plus 1 means h fn plus 1 means backward Euler. If we are taking theta is equal to 1 by 2, so in that case we are getting 1 by 2 g at xn plus 1 by 2 g at xn plus 1 means h by 2 fn plus 1. So then we are getting the trapezoidal rule.
Yes, sir. Convex combination type.
Yeah. So we have these known as the theta method. And if you see that for theta is equal to 0, it will be only explicit method, otherwise it will be implicit method.
Yes, sir.
Yeah, so error analysis we can discuss if you wish. We have 45 minutes, or we can discuss the linear multi-step method. Then we can move to, I will tell you the motivation for the RK method. So linear multi-step method. So in linear multi-step method, basically, we are using nth degree polynomial to interpolate the curve. Am I right? And the general linear multi-step method, k-step method, would have the form this: j is running from 0 to k, alpha j yn plus j is equal to h times summation j is running from 0 to k, beta j f x n plus j yn plus j. So it means that if you observe here, when what is unknown? Unknown is yn plus k, and we are using in the formula, we are using basically yn plus 0 means yn, yn plus 1, yn plus 2, and so on, yn plus k minus 1. And here also it is. So now if you see here that if beta k is 0, if beta k is 0, so then we will have explicit that yn plus k. In that case, if you just expand both sides on your notebook, just expand, so you will see that on the left hand side we have alpha 0 yn plus alpha 1 yn plus 1, and so on, alpha k yn plus k. Am I right? And on the right hand side we have h into beta 0 f n plus 0 means fn plus beta 1 fn plus 1, and so on, beta k fn plus k. If beta k is 0, so then we do not have in a term in the formula of fn plus k. So that's why we have the terms fn k plus k minus 1, fn k minus fn plus k minus 2, and so on. So that's why it is the explicit formula. But if beta k is not equal to 0, so in that case it will be implicit linear k-step method. Now, so we have already seen an example of two-step method, and here, so now whether we can write these trapezoidal or this one Adam-Best-Forth method. Because one-step method is also a particular case of multi-step method. Am I right? So
Yes, sir.
yeah, so we can write this yn plus 1 is equal to yn plus h times f n plus 1. So this is an implicit linear one-step method. Similarly, trapezoidal, because you see what is the value of alpha here. Here in single step method, what will be the value of k? The value of k will be 1. Am I right? So how many? So tell me can you just tell me what will be the value of these alpha j's and beta j's? Am I right? So it means that any multi-step method is specified by these alpha j and beta j's. So
Yes, sir.
yeah. So here, how many, if we change the value of alpha j and beta j, so we have different method. So how many value of beta j, alpha j, here we have k plus 1. Am I right? Alpha 0 plus alpha 1 plus and
Yes,
alpha 2 and alpha k. Similarly, we have beta 0, beta 1, beta k. So now tell me how many value in single step we have. We have k is equal to 1. So means alpha 0 and alpha 1. Similarly, beta 0 and beta 1. So tell me what will be the value of in implicit Euler method. What will be value of alpha 0, alpha 1 and beta 0 and beta 1? So can you please tell me? Hello? Just write down. First you should write down the journal single step method. So what form it has? It has j is running from 0 to 1, alpha j yn plus j is equal to h summation j is running from 0 to 1 beta j f n plus j. So please just write down. Just expand the summation. So we have alpha 0 yn plus alpha 1 yn plus 1 is equal to h times beta 0 f n plus beta 1 f n
Fn plus 1.
Yeah.
Fn plus 1.
Tell me for the implicit Euler method, tell me the value of alpha 0, alpha 1 and beta 0, beta 1.
So alpha 1 is 1.
Alpha 1 is 1, alpha 0 is 0 and beta 0 is
0.
beta 0 is
Beta 1 is 1.
and what is alpha 0? Hello?
Alpha 0. Alpha 0 is 0, sir.
Alpha 0 is 0. Okay, just write down the formula alpha 0 yn plus alpha 1 yn plus 1 equal to
Oh, sorry, sir.
Yeah.
Sorry.
minus
1.
1. Alpha 0 minus 1, alpha 1 is 1 and beta 0 is
Beta 0 is 0.
beta is 0 and beta 1 is
1.
and what will be the value of the trapezoidal method? What will be the value of these alpha 0 alpha, because that is also a single step method? Just tell me. This is the trapezoidal rule. Yn plus 1 is equal to yn plus 1 by 2h fn plus 1 plus fn.
Sir, so here beta 0 is 1 and beta 1 is beta 0 is half and beta 1 is also half. Alpha 0 is minus 1 and alpha 1 is 1.
And in Adams' Best-Forth method, what will be the value?
Beta 0 is 0 and beta 1 is also 0. And sorry, sir. Alpha 0 is 0.
Yeah, first you have to understand that what is the value of k for this one?
Sir, alpha 0 is 0, alpha 1 is also 0.
No. But first you should step what is the value of k. K is 4. The 4-step Adams Best-Fourth method. This one. So now if we write these, so what we need to specify: alpha 0, alpha 1, alpha 2, alpha 3, alpha 4. Similarly, beta 0, beta 1, beta 2, beta 3, beta 4. So just tell me the value of all these 8 parameters.
Sir, beta 0 is minus 9 upon 24. And beta 1 is 37
Tell me
upon
the value
24.
of alphas, then beta.
Alpha 0 is 0.
Yeah.
Alpha 1 is also 0. And alpha 2 is 1.
Alpha 2 is
1.
0.
0. Then okay, sir. Yeah. Then alpha 3 and alpha 4 is 1.
Yeah.
Alpha 3 is minus 1. Alpha 4 is 1.
Alpha 4 is 1. Now we come to the beta 0, beta 1. Yeah. Yeah. So beta 0 is minus. Yeah. Tell me.
9 upon 24.
Yeah. And beta 1 is?
Beta 1 is 37 upon 24.
Yeah.
And this is minus 59 upon 24.
Yeah.
And this is 55 upon 24. Sir, can we say they are the weight? These are the weight functions.
These are the
weight functions.
Yeah, we can say that. These are the basically we are taking a linear combination of these fj's. Am I right? We are taking basically combination of these f's, and we are giving a different weight. Am I right? Because you see, what is this? This is the value of f at xn. Am I right? This is the value of f at xn plus 1. So this is in that way we are taking, basically we are approximating the integral. So we are doing in that way, but in that way we have the different step. So now you see that what is the problem? I mean, by this you can say that in this way we have the method of order 4. If you take a k-step method, so then we have the method of order k. Am I right? A method of
yes,
order
sir.
k. So we are getting the desired order here. Order of convergence means error will be of order in this case would be h power 4. If you are using the method of means k-step method, so in that case we would have the error of order h power k. Am I right? So in that way we would be able to get rid of the drawback of these single step method. Am I right? Single step method only means Euler backward, forward, and trapezoidal method. But now you should ask that then why we go for these RK methods. But if you see when we were here, so when we are using this one, am I right? So to here, suppose we are here, we are using two-step method. This is the single step method. Am I right? So we are using this value and we are predicting. Am I right? In single step. In multi-step method, we are using this value and then we are predicting this value. Am I right? So of course order of convergence would be more, But what's happening here, if you observe, because this except this value y0, am I right? All are the approximate value. Am I right? This y1, y0 is the exact one because it is given. Y1 is approximate value, or this yn minus 1 is approximate value, yn minus 2 is an approximate value. Am I right? So now you see that when we are dealing, when in single step method, so approximate value means we are, the value is with has the bug. Am I right? So we are using this one, the bad value, I can say that, or bug. And when we are using two steps, so then we are using the two value which has the bug. So it means that can we obtain a method of order n only using a single step? So the answer was given by Runge in, I think, 1896. 1896, he gave the affirmative answer. Yes, we can do that. We can generate a method of order n with I mean using a single step only. And what he did, basically he introduced some fictitious node, and then he took the weighted average of that, and in that way he generated the Runge-Kutta method. So we are just coming out that we will also discuss. I will give you overlook, and I will give these notes. So if you would be able to, anybody interested, these are very interesting notes, so you can see. So in they have discussed the error analysis also, so we are not going for that. So in that way, basically in Euler method is only first order accurate. Nevertheless, it is simple and cheap to implement, because to obtain yn plus 1 from yn, we only require a single evaluation of the function f at xn yn. Runge-Kutta method aim to achieve higher accuracy by sacrificing the efficiency of Euler method through re-evaluating the f at points intermediate between xn yn and xn plus 1 yn plus 1. So they have taken the intermediate fictitious node, and they choose that node in such a way that we get the desired accuracy. Am I right? And these are two mathematicians, if you remember, Runge and Kutta. Runge developed these method for the scalar initial value problem, and Kutta in 1900, around 1900, extended these method to a system of first order initial value problem. So that's why later this is known as the Runge-Kutta method. So in that case, how we develop the method, yn plus 1 is equal to yn plus h times this phi xn yn and hn. So this phi xn yn, basically this is the approximation of the integral. So basically we are approximating the integral by the summation. Am I right? And we are taking these CR, taking these CR, KR, where K1 is F, KR is given by this formula, and we have generated the intermediate node by this X plus HAR, and these A, we are taking A in such a way that this lying in the single step in between xn and xn plus 1. So these are the Rangakuta method. So if you look one stage Rangakuta method, suppose that R, capital R is equal to 1. So then the resulting stage Rangakuta method is simply Euler explicit method. You look here, you take capital R is equal to 1. Capital R is equal to 1. So we have this only, we have only C1, K1. C1, K1, and K1 is equal to F X Y. So basically F X Y means Fn, F at Xn, Yn. So we have this Yn plus 1 is equal to Yn plus H F Xn Yn, and C1 we are taking 1. Now if two-stage Rangakuta methods, so in this case you consider R equal to 2. So R equal to 2 means Yn plus 1, Yn plus 1 is equal to Yn plus H C1 K1 plus C2 K2, where K1 is equal to F Xn Yn, K2 is equal to F Xn plus A2H, Yn plus B21 H K1. So and where the parameters C1, C2, A2 and B21 are to be determined. So how many parameters to be determined in two-stage Rangakuta? This is not Rangakuta method. You see, it is a class of methods. Am I right? So here, how many parameters we have? 1, 2, 3, 4. 4 parameter we need to determine. So if you see if we write these 3 equation in the form, just put the value here, Yn plus 1 is equal to Yn H Fn Fxn Yn plus C2 Fxn plus this one Yn plus this one. And then how we will find out the value of these means C1, C2, A2 and B21? So we need, how many relation we need? We need relation, four relation we require. Am I right? One relation is C1 plus C2. C1 plus C1 plus C2 is 1. So this is coming from the fact that the method will be consistent if and only if. When we say that a method, this type of method, I mean, is consistent. This we say that the method 22 means the linear multi-step method. The single step, journal single step method is this one. This is the form of most a journal explicit one-step method may be written in this form, or we can say that this is the most general form of explicit single step method. Am I right? So this method will be consistent if and only if, using some analysis, it's a analysis, if and only if and only if phi x0 y0 means h0 must be fxy. So what is phi in this case? Yeah. So this is two stage. So what is phi here? If you see, phi is this one, C1 K1 plus C2 K2 means C1 F plus C2 F xn plus A2H comma yn plus P21 H1. Now put H equal to 0. So then what will be phi if we put H equal to 0? So then we will have C1 F xn yn plus C2 F xn yn, because this component will become 0, this will become 0. So we need for the consistency, what we require that H times C1 Fn plus C2 Fn means C1 plus C2 Fn is equal to Fn. So from this relation we have C1 plus C2 is equal to 1. So we have, because we need to have the method is consistent. So one condition we will have from this. Other three conditions we need to have more. Further condition on the parameters are obtained by attempting to maximize the order of accuracy of the method. Indeed, expanding the truncation error. So basically, what is truncation error? So truncation error is in the, yeah, this one is the truncation error. And in truncation error, what we used to do, we used to expand these all the xn plus 1 or xn plus 2 fxn plus 1 in around xn. We wish to remove these xn plus 1 wherever it would be. So in this case, so expanding the truncation error, wherever it is, I mean there. So this is the first one which we have, and the second is this one, this phi. When we subtract phi, so we will expand this around, we will expand f around xn and yn. So then if we do that, so we have this formula. So if you do the calculation, so we have this one, and from here we are subtracting that value. So now we need to have conditions. So how we will need to have conditions such that as much as h terms will cancel out. So what is this y double prime xn? Y double prime xn, we can find out y prime is f. So take y double prime will be f curly fy or fx plus fx plus f into fy xn. Am I right? Similarly, you can find out this y triple prime, and then we use f we are using for f xn comma y at xn. Fx we are using curly fy curly x, and y double prime will be okay. They have calculated in that way. So now if we look here, compare this one and this one. So h times c2 a2 plus c2 b21 fy. So here also we have 1 by 2 h. If we put the value of y prime from here, so fx plus fy y. So now if you compare, because we want that these should be the equal, so that's why both will be cancel out, and then we have the term in truncation error, the minimum order term h square. So that's why we will choose c2 a2 and B21 in such a way that these two terms matches. And to match that, so what we require that C2A2 must be 1 by 2. So that here we have 1 by 2 H, and C2 B21 again it should be 1 by 2. So then we will have again 1 by 2, and we will take 1 by 2 cancel outside, and then this will be cancel out. This thing is clear. So then we have terms of order in terms of order H square for any F. So from here you see that how many condition we have. One condition we have from here, two condition we have here. So we have three condition, and how many unknown we have? We have 4 unknown. So we have the rectangular system of equation. Am I right? So we do not have the square system. So to make a square, so one parameter we need to have free parameter. Am I right? So that's why we use the different value of that parameter. So you will have different value of two-stage method. So that's why it is known as the means two-stage or R stage Rangakuta method, not a methods. So if we which implies that if we take B21 is equal to A2, if we take B21 is equal to A2, so then we have C2 is equal to we are assuming that B21 is equal to A2, then C2 have 1 by 2 A2, because we are keeping A2 as a free parameter. So all the value we will calculate in terms of A2, and C1 is coming out to be, just to put the value here, so C1 is coming out to be 1 minus 1 by 2 A2. So then the method is second order accurate, while this still leaves one free parameter A2. So it is easy to see that that no choice of the parameter will make the method generally third order accurate. So there are two well-known example of second order Rangakuta method. What are these example? If you see, if we take A2 is equal to 1 by 2, A2 is equal to 1 by 2, A2 is equal to 1 by 2. So then you will find all the value of B21 is equal to 1 by 2. Then C2 will be equal to 1. C2 is equal to 1, and then C1 also C1 will be 0. Am I right? So then if you put the value here, so then we will have this modified Euler method. If we take A2 is equal to 1, so then we will have improved Euler method. You can just verify. I will send these notes to ma'am, and she will circulate. So in that way we generate this one. So I think I should stop here. So anybody have any query? Hello.
Yes, sir. Any queries from the participant side? So I hope everyone has really explored the detailed concept about all the discussions.
And
so we are very thankful to you, sir.
Yeah, I have just mail you these notes also. You may circulate them to the participant if anybody interested. So if he or she study at the later stage also,
right, sir.
Then also I can clear the doubt. For the So these are, I mean, very good notes for initial value problem. These are based on the book by Lambert
Okay, sir.
and made by Professor Andre Suli. He's a renowned numerical, numerical analyst at the Oxford University.
Okay, sir.
So it's fine, I think.
Right, sir. So thank you very much, sir, for sharing these documents with us, and we will share with this all the participants so that they can explore it in a very detailed manner.
Yeah, and if anybody go through these notes and face any problem, so please don't hesitate to contact me.
Right, sir.
Thank you,
I
sir,
will be
for
happy
this.
to answer. And
Thank you very
if you are teaching reading the methods for initial value problems, so please do consult these notes. These are wonderful notes, and I hope you would at least maybe I don't know how much you received from my lectures, but at least these notes are wonderful. Whenever you will teach or study, so these are useful. Okay, thank you.
Thank you very much, sir. We are
Thank
really
you,
very
sir.
thankful to you for sharing these notes. I hope all the participants will be able to use this in academics as well as for research purpose also. And moreover, we are also very thankful to you, sir, for sharing your profound knowledge and expertise about differential equation with all the participants. And you cleared each and every step in a very detailed manner and in a very interactive manner. So I hope all the participants have really conceived the session content in an elaborate manner. So thank you very much, sir. And I am really thankful to all the participants. I am extend my thanks to all the faculty members of Department of Mathematics and our head of department, Professor Alka Tripathi ma'am, for giving her time and support to us for the smooth conduction of this event. So tomorrow again, we will connect with the same link at 3 p.m. for the next expert session.
Okay, thank you, ma'am, and thank you all the participants for being present. Okay, thank you.
Okay, thank you, sir. Thanks to all.